So moving towards factor analysis. Now, before we move further, let me say that I don't think we have much time to cover both factor and cluster, but I'll try my best to cover both at as fast pace as possible, trying to ensure that everyone understands as much as possible. So before we get into factor analysis, we've already completed much of PCA. And let me tell you that PCA and factor analysis are basically two sides of the same coin. Okay. In PCA, we are basically looking at dimension reduction and orthogonalization of the variability of the of the variables at hand. Whereas in factor analysis, we are more interested in finding commonalities or and uniquenesses of variables in such a way that for each principal component that we found, let's say in PCA, what happens when, let's say for one principal component, only a subset of the variables are highly correlated or have a high, let's say, assimilation towards one particular factor, and that subset of variable does not have that same affinity towards the other factors or other principal components. Which means that for each principal component, you will have a unique set of variables that will have a very high affinity towards that particular principal component. If that happens, it means that every principal component that you have is basically talking about only a subset of the factors or the subset of variables that you are having. So instead of trying to reduce the number of variables in the dataset, you are trying to group variables. So a very good example of this can be given in a very short context. Let's say I am taking 5 different examinations of students, and 5 of these examinations are such that 2 mathematics-based papers are there, 2 English-based papers are there, and one, let's say, one science physics paper is there, right? So obviously, in the maths paper, let's say we have number theory and set theory. In the English paper, let's say we have literature and grammar. And in the physics paper, let's say we have thermodynamics. So if we look at 5 of the scores obtained by each student in each of these papers, we will individually, if we look at these papers, then they are individual variables. But if this information is already presented to us, that number theory and set theory are, similar, those who fare well in number theory and set theory are students who are generally better at math. There will be students who are generally better at literature and therefore generally better at English, and therefore they will get better grades in literature and in grammar. And obviously there will be some students who are better in physics and they'll be faring better in thermodynamics. If this information is not presented to us or not presented to the computer, let's say, or to the invigilator, he might look at these papers independently as independent variables. But for the person who has set these exam, he knows or she knows that 2 of these papers are related to mathematics, 2 of these papers are related to English, and 1 is related to physics. So instead of looking at it as 5 different independent papers, the examiner might look at it as an examination of 3 different disciplines: 1 of English, 2 of mathematics, and 3 of physics. So in this way, if we look at this same dimension reduction problem as a way of grouping variables such that similar variables are grouped together, then that kind of analysis is known as factor analysis. Okay. Now, let us get into some of the basics. Factor analysis is a general name denoting a class of procedures primarily used for data reduction and summarization. Let us start from here. Yeah. Again, this is an interdependence technique, which means that we are only looking at examining interdependent relationships between dependent and independent variables without making any distinctions. And it is used in these circumstances, first to identify underlying dimensions or factors that explain correlations. It can also be used to identify new or smaller set of uncorrelated variables to replace the original set of correlated variables in subsequent analysis. So as I said, instead of 5 papers, if we are talking about 50 different papers in 50 different topics, where actually 10 of these topics are pertaining to one individual subject, then it is better to work with 5 variables of each discipline rather than 50 different papers of the same make. So instead of having to work with the score of 50 different papers, topical papers, you only have to look at scores from particular discipline or from particular subject. Uh, and another circumstance in which factor analysis might be used is to identify a smaller set of salient variables from a larger set for use in subsequent multivariate analysis. So in that case, maybe there might be certain cases where, let's say, for example, in marketing research, this is a very highly coveted tool, factor analysis, in order to understand which bracket of customers or which customer to group in which particular area. So let's say, for example, there is a psychometric test based on the buying behavior of a consumer. Like say, for example, if I am to sell toothpaste, and before selling toothpaste, I am asking the consumer 5 different questions, right? And 5 of these different questions might be pertaining to different kind of consumer behavioral pattern. So one might be that, let's say, I am asking the person whether or not they agree that a toothpaste should be such that it makes your breath smell nice. It should make you more accessible or more attractive to other people. Another set of questions that can be set on based on this premise is that, let's say, toothpaste should always be cheap, right? It should not interfere with the buying behavior of some other commodities, or let's say toothpaste should be between this and this price range. Another set of questions that can be inserted here is that, let's say, a toothpaste should be one that manages your oral health efficiently, one that keeps your gums healthy and your teeth whiter. So as you can see, 3 of these types of questions, although there are multiple questions in each type, there is a similar thread going on. So in the first thread of questions, I am already pitching the toothpaste as a way of looking attractive or feeling attractive within oneself. The second bracket of questions that I am asking to the consumer is more relevant on how they are looking at it economically, or whether or not they are looking at the toothpaste from a financial point of view, as a commodity in which finance is of interest. And thirdly, I'm asking them whether or not they see it as a medical tool or something that might aid their dental health. So because buyer behavior is somewhat undeterministic, therefore different people will focus on different aspects of these questions, and thus we might be able to bracket a consumer as whether or not they look at toothpaste as a means of feeling attractive, or as a means of saving money, or as a means of simply living a better, healthier lifestyle. So again, instead of having to focus on each and every question separately, we can simply group these variables and take a consolidated score and use those consolidated scores for further analysis, rather than just take individual questions and their answers. Right? Now, mathematically, each variable can be expressed as a linear combination of underlying factors. And so this is what the factor model looks like. So this, if xi is a variable, it should be written as a linear combination of all the factors, where ai are the standardized regression coefficients of the variable I or on the common factor j, and the f are the common factors, the factors that are linked to the ith standardized variable. Right? Here, vi is the standard regression coefficient on the unique factor I, and ui is the unique variable factor for variable I. So if you recall, in the last session, we had discussed that within the data set, there is a severe overlap. There may occur a severe overlap of variability, right? And it is because of that there is a space called commonality and that of uniqueness. So in this diagram, as you can see, the uniqueness of X4 is given by the green segment. This is the segment where X4's variability is not overlapped by X1 or X2 or X3. Similarly, In the region that I am highlighting right now, this region, let's say, this is the region where x4 has some commonality with x2, but not x3 and x1. This is the area where x4 has commonality with x1, but not x2 and x3. This is the area where x4 has commonality with x3, but not x2 and x1. This is the area where x4 has commonality with both x1 and x2. And this is an area where there is commonality between x1, x3, and x4. Correct. So in this way, we can see that x4 has the total variability of x4 can also be differentiated into what kind of variability x4 has on its own, and how much of that variability is shared with x2, x1, x3, and combinations of the same. Right. So coming back to this, M here is basically the number of common factors that we are taking. Now in factor analysis, before we proceed further, there are two types of factor analysis that we know. One is confirmatory factor analysis and one is exploratory factor analysis. Confirmatory factor analysis entails that we already know what the groups of these variables are, and we are only looking to find out what best way to assign scores to these groups. Right? We are looking at the scoring pattern. We are looking to find an optimum or an efficient scoring, let's say a score based on the groups. And in case of exploratory factor analysis, we are looking to group the variables in the first place and then go to the scoring. By the name only, it is already, I think, open that in exploratory analysis, we do not know which variable belongs to which factor. So we first need to judge which group that particular variable goes to, and after the groups are made, then we decide what the scores will be. Now, because each variable can be written as a combination of all the factors and its own uniqueness, similarly, all factors also can be written as some as a linear sum of, or a weighted sum of all the variables that we have. So Fi is the estimate of the ith factor, Wi is the weight of the factor score coefficient, Xi obviously is the ith variable concerned, and K is the number of variables we have. Now it is possible to select weights or factor scores so that the first factor explains the largest portion of total variance. So how do we do that? We use the eigenvalues as we have done in the previous case, that is in principal component analysis. Similar to that, the second set of weights can be selected so that the second factor accounts for most of the residual variance. Again, it is because the largest eigenvalue or the largest the eigenvector corresponding to the largest eigenvalue will have the largest variance. The eigenvector corresponding to the second largest eigenvalue will have the second largest variance, and so on and so forth. Now, similar to that of, let's say, in our factor analysis case, even in our principal component analysis, in factor analysis also, especially in case of exploratory factor analysis, it might be required that how many factors do we need. In case of confirmatory, although it is already known, but in exploratory factor analysis, it is it is also a cause of concern, because if there are too many number of factors, then there is a possibility that some variables might be misclassified into some other group, or maybe some groups may be broken down into subgroups because the number of factors that were allotted were not correct. So correct number of factors to be taken should also matter here, right? For that, again, we use the Bartlett's test of sphericity in this case, as we can also do in PCA. But we have used a scree plot there also. Here also visually a scree plot may be used, as we will see later on. Another way to look at that is through the correlation matrix. Right, it is a lower triangular matrix showing the simple correlations between the possible pairs of variables included in the analysis. Obviously, this is by lower triangular, not just low. It is a symmetric matrix, basically the correlation matrix, where the upper triangle is a mirror reflection of the lower triangle, and the diagonal elements are all one, and the non-diagonal elements are symmetric. Now, the communality is the amount of variance a variable shares with all other variables, as we have discussed earlier. It is that eigenvalue is the total variance explained by each factor. Again, here the definition of eigenvalue here is purely in context with factor analysis. Okay, mathematically, eigenvalue has a lot more geometrical interpretation associated with it, but we will not go there. You can take this as a contextual definition of eigenvalue purely in the context of factor analysis, that it represents the total variance explained by each factor. The factor loadings are simple correlations between the variables and the factors themselves. And we will also look at a loading plot where we will look at how much loading the original variable has to a particular factor, right? And similarly, we will also look at a factor matrix, which contains the loadings of all variables and all factors extracted. And basically, on the basis of factor matrix only, we'll see how a factor loading plot is made. Factor scores are composite scores that are estimated for each respondent of the derived factors. Another way, as I said, another way of validating whether or not factor analysis should be done or not is by looking at the Kaiser-Meyer-Olkin estimate or measure of sampling adequacy, which is the MSA. Right. MSA can be calculated for all individual variables. A general rule of thumb is that if the MSA is above 0.7 for all variables and KMO is greater than 0.6 or 0.7, then factor analysis is okay. It is the dataset is suitable for doing factor analysis. Generally, if it is very low, lower than 0.6, we do not necessarily believe that it is factor analysis should be the way to go. In that case, some transformation or some kind of more pre-processing might be required. In this case, high values indicate between 0.5 and 1, but there are certain people who believe that anything below 0.6 is not good enough. But again, those are rules of thumb that depends on how much precision the researcher is willing to impose. The percentage of the total variance attributed to each factor, that is also something that can affect the number of factors you want, right? So let's say if I want 90% of the total variability, and based on that many factors I will need. Same as in principal component analysis, what we have done, we will do the same thing here. That can be done, does not mean that should be done. Again, it depends upon the situation and the need of the hour at that time. Residuals are the differences between the observed correlations as given input correlation matrix and the reproduced correlations as estimated from the factor matrix. So from the factor matrix also, we will be estimating reproduced correlations, and the difference between the observed correlations and these reproduced correlations are known as residuals here. Mind you, this is different from the context of residuals what we look at in linear regression analysis. Here the residuals basically are in the context of correlations. And scree plot, as we have seen in earlier in PCA also, scree plot is the plot of eigenvalues against number of factors. Now, let's say we have this data and we have collected on a Likert scale, right? Likert scale means a 7-point scale. So this is scale data on V1, V2, V3, V4, V5, and V6. And let's say these are all questions that have been given, and the questions have been recorded on an agreeability scale. All right, so V1 is, let's say, question number 1, and respondent number 1 agrees wholeheartedly. So he's extremely agreeable to, let's say, the first to this statement V1. He is more or less neutral to number 2. He is agreeable to number 3, somewhat agreeable to number 4, somewhat disagreeable to number 5, and somewhat agreeable to number 4. Right. And similarly, from respondent number 2, you can see that he's severely disagreeing to number 1, statement number 1, neutral towards number 2, and so on and so forth. So as you can see, you go to different respondents and ask them the same question, their reaction or their agreeability to whatever statement you make will be different. And so that has been recorded. So let's say this is one type of market study that they have done. Now, how to conduct factor analysis? So the first thing that you do is the formulation of the problem, right? So how to formulate the problem? The objectives of factor analysis should be identified, and the variables should be included in the factor analysis, and they should be specified based on either past research or theory, or based on the judgment of the researcher. It is important that they be measured properly, right? Either on an interval scale or on a ratio scale. Again, they cannot be categorical in nature, as we have already discussed in case of PCA. An appropriate sample size should be used as a rough guideline, at least 4 or 5 times as many observations as there are variables. So if you are working with, let's say, 10 variables, there should be at least 40 to 50 samples available. But again, that is a rule of thumb. There are other researchers who have published based on certain other tables. There's the Tracy Morgan tables and many other tables available, which tell you what sample size to take based on how many variables you have and what type of scaling is done. Right. So there are those things as well. Now, when we look at the correlation matrix, this is what it looks like. However, this minus 5.3 will be replicated here. Basically, this is not just a lower triangular matrix. These the empty cells also is a mirror image of the lower triangle. Okay, the empty cells here are a mirror image. So minus 5.3 should come here also. Minus 0 plus 0.873 should be here. Here it will be minus 0.086. Here it will be minus 0.858. Here it will be 0.004. Similarly, so on and so forth. Now, how to construct the correlation matrix? This we all know. But after we construct the correlation matrix, the Bartlett's test of sphericity must be used so that the variables, we know whether the variables are uncorrelated in the population, right? Because if this hypothesis cannot be rejected, then maybe factor analysis cannot be done. Okay. Another useful statistic, that is the Kaiser-Meyer-Olkin measure of sampling adequacy. Again, smaller values of KMO means that it will be inappropriate to use factor analysis. We need higher values. Obviously, it should best it is greater than 0.6, 0.7. If it is between 0.5 and 0.6, based on your judgment, if you want to keep, you can keep. If you want to discard, you can discard. But if the KMO statistic is coming out to be less than 0.5, then I would, at least in general theory, it is not recommended that you go forward with factor analysis. Now, how to conduct it? Now, the method of factor analysis can be, there are many methods to extract factors. One of them is principal component analysis. And here we have already deduced that. There is common factor analysis, which is factor estimated based on only the common variance. But here, this is also known as principal axis factoring. Here, the commonalities are inserted in the diagonal of the correlation matrix. Okay, so here basically your commonalities are given in the diagonal. So this looks more like a covariance matrix, but is actually a correlation matrix with commonalities coming in the diagonal. Now, this is appropriate when the primary concern is to identify this underlying dimension and common variance. But in PCA, we generally we will be using the correlation matrix itself, right, without touching its diagonals. So, based on the data that we have seen earlier, let's say these are the results of the principal component analysis. So, here are the commonalities. So, variables V1. The initial was 1 and the external 0.926 has been extracted, right? So out of 1 total, 0.926, which means the commonality of variable 1 is only 0.014 or something like that, right? 0.084 or 0.074. And similarly on variable 2, variable 3, as we can see, extraction is high. So there is a lot of commonality of these variables there. Here, the eigenvalues, as you can see, the first factor's eigenvalue is 2.7, second factor 2.2. From the third factor, it becomes 0.442, 0.341, and so on. So the percentage of variance, if we cumulate it, you can see that if you want 90% of the variability, you have to take four factors. If you are happy with 89 or 85%, then 3 factors are enough. If you're happy with 80% variance, then 2 factors are enough. But if you go below 2 factors, you will end up with only 45%, which is less than half of the variability, which is not particularly recommended. Now here are the extraction sums of squared loadings. So what this tells you is that, let's say we have taken only 2 factors, right? We're having 82%. So you have 82% of the cumulative loadings, and again, because we have taken only 2 factors, that is what it will take. Now here is the factor matrix. So under factor 1, you see that variable 1 has 0.928. So this is the correlation coefficient between variable 1 and factor 1, which means that variable 1 has this much contribution in factor 1, which is a very high contribution. Also, variable 1 and factor 1 are positively correlated, which means that higher value of variable 1 means factor 1 is also a high value. But in case of variable 2, as you can see, factor 1 has very low value as compared to factor 2. Factor 2 here is very high, 0.795, which means that variable 2 has more contribution in factor 2. Similarly, in variable 3, as you can see, it has more contribution in factor 1, right? Variable 4 has more contribution in factor 2. Variable 5 has more contribution in factor 1, but in a negative contribution, right? Although it is negative, it is high contribution, no doubt about it. And variable 6 has more contribution in factor 2. So we can say that variable 1, 3, 5 are more powerful in factor 1, or they are basically the influencers of factor 1, and variable 2, 4, and 6 are actually more influential in factor 2. So these are the variables that decide what values factor 2 should take, as opposed to V1, V3, and V5, which are more influential in what values factor 1 takes. Okay. Now we will look at the rotation sum of squared loading. So after we have done a rotation, right? By rotation, I mean we are simply rotating the variances around, the communality variances that we had. We are simply rotating them around in such a way that those variables that have a heavy loading in particularly one factor will have smaller loadings in the other factors, and those variables having higher loading in those factors in the second factor will have smaller loading in the other factor. So as you can see, let's say variable 1 has very high loading in factor 1, but it has 0.253 loading in factor 2. So if I were to take some of this variability from this 0.253 and I were to inject this in factor 1, right? So in that case, factor 1 would increase, the loading of variable 1 in factor 1 would increase, and the loading of variable 1 in factor 2 would decrease, which means even a clearer demarcation that V1 should be in factor 1. So here we are looking at that. Here we are looking at how to even make clearer this demarcation that this variable belongs to this factor. The more clearer it is, the more better your factoring is. Am I clear? Yes. Is this hard to understand?
Yes, sir.
Okay, I'll repeat myself then. If the loading of one variable on one factor is very high and the other factor is very low, what does that mean? It means it is easier for you now to bracket or group this variable under factor 1 rather than factor 2. Yes.
Yes.
If let's say variable 1, if it has correlation 1 with factor 1 and correlation 0 with factor 2, what does this mean? That factor 1 पे ही पूरा जाना चाहिए. It should go wholly towards factor 1, that
Right.
group. Why? Because we are increasing the loading in that factor in which the loading is already high, and we are decreasing the loading in the other factor where it is already low. So the demarcation is increasing. No, the difference is becoming even clearer that this variable should go into that factor. And actually, that is the objective of factor analysis or rotation, that to make this demarcation clearer as to which variable should go under which factor. Okay. So after rotation, as you can see, once it has been rotated, now you can see here V1, it under factor 1 it has 0.962, but under factor 2 it has been reduced to 0.027. So as you can see, the demarcation here is even more clearer than before, right? Yes or no? In the previous case, it was 0.928 and 0.253. Now it is 0.962 and minus 0.027. So because this is very, very close to 0, we can say that V1 is almost orthogonal to factor 2. It has no influence on the factor 2 at all, but it has a lot of influence on factor 1. So that is why we will group V1 into factor 1. Right?
Yes, sir.
Yes.
Clear.
Yes. Similarly, variable 2, if we see before, it had minus 0.301 and 0.795 in factor 2, but now the demarcation has been made even clearer. It is now minus 0.057 for factor 1 and 0.848 for factor 2, which means that V2 is more inclined towards factor 2 than factor 1. Right. Similarly, for we can see for V3, for V4, for V5 and V6 also. Okay. So as we had said before, V1, V3 and V5, they are for factor 1, and V2, V4 and V6, they are more stronger in factor 2. Okay. Now the same for the factors for coefficient matrix. The coefficient matrix is basically the model, right? So how does this model take place? That if I want to make factor 1, then in that case F1 is equal to 0.358 multiplied by V1 minus 0.001 multiplied by V2 plus 0.345 multiplied by V3 minus 0.017 multiplied by V4 minus 0.35 multiplied by V5 plus 0.052 multiplied by V6. Similarly, factor 2 model will sound like what? 0.011 multiplied by V1 multiplied by 0.375 multiplied by V2 plus, minus 0.043 multiplied by V3 plus 0.377 multiplied by V4 minus 0.059 multiplied by V5 plus 0.395 multiplied by V6. So this is just the coefficient of the model that we wanted. As you can, in the previous one only, I think we have already covered that. Where is it? Yeah, this one. Right. So for F1, this is AI1, AI2, AI3, AI. Those are the coefficients. Okay. Okay. So now the factor score coefficient matrix looks something like this, right? Where V1, V2, V3, V4, V5, V6, as you can see, these red marks here, these are not the correlation coefficient or anything like that. These are the scores, the loadings. Okay. These are the loadings, as you can see. And for V2 also, as you can see, 0.723, eight four eight something. Okay. Okay. I think there was factor 1, factor 2, something like that. These are the variables V1, V2, V3, V4. I think there has to be F1, F2, S3, F3, F4, something like that. Okay, nothing to worry about. Okay, now how to determine the number of factors, right? So first is a priori determination, means pehle se pata tha. I mean, it means that it was known from beforehand only. Okay, so due to prior knowledge, the researcher might know already how many factors to expect, and he can specify. And the second is based on the eigenvalues. So let's say either you can take in this rule, which is very prevalent in SPSS, that as long as the eigenvalues are greater than 1, you can take. Once eigenvalues are less than 1, then stop taking. That is one rule you can use. Another rule you can use is based on how much variability you want. So let's say if you want 90% variability, so up to 90%, however many number of factors are there, you take that much and then leave. Right? Or on the basis of scree plot. So again, these are basically all the ways in which you can determine the number of factors, and percentage of variance we already discussed. Now the scree plot looks something like this. This is an elbow plot, as you can see. In the lower elbow, the part before which the thing becomes linear. As you can see in the bottom one, this becomes linear after number 3. All right. So in this case, 3 components are required. Why? Because after three components, this becomes a linear trend, right? So before it attains linearity, when was the last time the elbow broke? That will be the number of components that you need. Okay. Now there are many other ways in which you can try to determine the number of factors. One of them is on the basis of split half reliability, right? So basically, the sample is split in half, and factor analysis is performed on each half, right? So, and then let's say those factors which have high correspondings of loadings across two subsamples, only those are retained, others are left. You can also do that based on significance tests. So basically, we can simply do it, let's say, on the basis of uh, some chi-square test or something like that. Uh, Eigenvalues can retain only those factors that are statistically significant. So one of them is, let's say, the Bartlett's test, right? Which again, ironically, has a chi-square statistic. So there again, you can use tests like that to actually make this decision as to how many number of factors will be optimum. Uh, Now, how to rotate these factors? Again, although this initial or unrotated factor matrix, they also show us a lot of things. Means that they indicate the relationship between factors and individual variables. But what happens is sometimes it results in factors that can be interpreted because factors are correlated with many variables, right? Because the factors are highly correlated with many variables, the interpretation it might be a little problematic, right? Therefore, through this rotation, what we do is we, as I told earlier, that we try to increase the gap by simply allowing more variability to the component that has higher variability in a particular factor, and removing that variability from another factor, which might result in it being classified or grouped under that factor. So by rotation also sometimes the factor matrix is transformed into a simple one, and obviously that will be even harder, easier to interpret. Right. Now, by rotating these factors, we would like each factor to have non-zero or significant loadings or coefficients for only some of the variables. Right. Also, we would want each variable to have zero or significant loadings with only a few factors, if possible, only with one. And any rotation is orthogonal if the axes are maintained at right angles. So that is basic. And the most commonly used method that we have used and we will use in Python also is called varimax. Okay. Again, as the name says it all, maximizing the variance, right? That is varimax. Where are you maximizing the variance? In the factor that it is already maximized, right? So if maximum portion of your variance is in factor 1, we will maximize that variance further and reduce the variance in factors where your variance was there, right? So that is known as the varimax procedure. The other kind of rotation that is common is called oblique rotation. Here the axes are not maintained at right angles, and even the factors are not correlated. Sometimes, just allowing for these correlations can simplify this pattern matrix. Again, oblique rotation is more used when principal axis method is used rather than principal factor method. Now, how to interpret these factors? So it can be interpreted in terms of variables that have high loadings. So as I told you in the previous in this example only, variable 1, 3, 5, right? They have very common loadings, right? They have very high loadings in factor 1 and very V2, 4, and 6. They have high loadings in factor 2. So if I want to interpret factor 1, all I need to know is about uh, its counterpart, right? By its counterpart, I mean if I want to know about factor 1, I will need to know about variable 1, 3, and 4, 1, 3, and 5. So if I know about variable 1, 3, and 5, I know what this does, right? This factor does. Similarly, if I know what let's say a 2, 4, 6 does, right? So I can easily predict what this will be like. So based on that, I mean factor 2 will be like. So based on that, as I said, that the factor can be interpreted in terms of variables with very high loadings on it. Okay. Another useful aid in interpretation is to plot the variables using the factor loadings as coordinates. So you can use the factor loadings as the coordinates, and yeah, you can plot the variables. Now, there are certain cases where high loadings are only on that particular factor, and of course also they describe the factor, right? Now let us look at a factor loading plot. So here, as you can see, in the component 1, V6, V1, and V3 are negative, but V2, V4, and V5, right, they are positive. In case of component 2, however, V1, V2, V4, and V6, right, V2, V1, V2, V4, and V6, right, these are the four. So they will be in they'll be rotated space component 1, and from the other angle, if you look at it, let's say V2, V5, and V6, V1, V3, right? So based on that, if we now make a rotated component matrix, it will look something like this. As I told you, because V1 has very high component on this, so in second component, yeah. Now for the ith factor, the factor scores are something like this. Yes. What happened? Am I audible?
Yes, sir.
Yes,
Yes.
sir. Yes,
Yes,
sir.
yes, yes. I don't know what happened, Achanak. Yeah. Okay. So now this is the rotated component matrix. As I said, after rotation, as you can see, the second component's load was even lighter, right? And here again, the second variable's component is also very small in the first compartment, which means that more variability of variable 2 is common with of component 2, right? And similar for V3, I see that uh, component 1 is a better choice, right? But for variable 4, however,
Component four.
yes, here 0.854 component 2. Why? Because E minus 02 means 0.09, something like that. E minus 02 means multiplied by 10 raised to minus 2. Okay. So because of that, this becomes minus 0.098. So that is why 0.854 is more. Similarly, V5 in V5, component 1 is more, and in V6, 0.885 is more. Correct. Now, by examining this factor matrix, we could also select each factor with the variable with the highest loading on the vector, and then that variable could be used as surrogate variable for the associated. But let's say if you have two or more variables and both of them have very high loadings, then in that case, the choice between these variables should be based on theoretical and measurement considerations, right? Which means that you need to go and check, and even double check sometimes. So because of that, this happens. Now, how to determine the model fit? Now, the correlations between the variables can be reduced or reproduced from the estimated correlations between the variables and its factors, which means that we have the variables, we have the factors, and based on that information, whatever we can do, right? That we're trying to do. Now, the differences between the observed correlations, which is given in the input correlation matrix, and this reproduced correlation, as we say, which is estimated from factor matrix. This can be examined to determine the fit of the model, right? And this will be known as residuals. Again, we have already done this in context to our previous previous session. Now, some results are given here. Obviously, Bartlett's test of sphericity is given here. The degrees of freedom here is 15. Yeah, but there is no significant difference. Okay, so as you can see, the significant test of significance is 0.000, which means they have rejected the Bartlett's test of sphericity. And Kaiser, Olkin, Chisler. Okay, so the KMO tells us that the data set is suitable for factorialism. Okay, okay. Now let us go back. Yes, hello. Okay, so coming back. Now from the loading themselves, we can now make the factor matrix, and this is what the factor matrix looks like. Right. This we've already, I think, covered a bit. Let me just. Right. So this was the initial factor matrix that we had. Hmm. Okay. So as you can see, this is the factor matrix without rotation. This is after rotation. This we've already covered. So yeah. Now let us go to Python. Quickly, let us get. So again, before we begin, we need to know what is the difference between PCA and factor analysis. In the PCA, components explain the maximum amount of variance, while factor analysis explains the covariance within the data. Okay. PCA components are fully orthogonal to each other, whereas factor analysis does not require factors to be completely orthogonal. Okay. Uh, there may be non-orthogonal factors as well, but those are special types of factor analysis. Uh, yeah, so the PCA component, it is basically a linear combination of the observed variable, while in FA, the observed variable, I mean, in vector analysis, the observed variables are linear combinations of the unobserved variable or factor. So, which means that whatever observed variable we have in FA, or if in our exploratory factor analysis, TCA component is a linear combination of the observed variables, right? Now, if there is any other observed variables that are linear combinations of the unobserved variable or factor, so then they might in that case even it will be FA, it will not be PCA in that case. Also, in PCA components are uninterpretable, right? Whereas in FA factor analysis, underlying factors are labelable and interpretable. So in that way, this PCA it is kind of a dimensionality reduction method as well. Okay. Now let us talk about the data set. Yeah. Here, I think we have already been supplied the data set called the BFI.CSV. Has everybody gotten the data set?
Yes, sir. We have received.
Yes. So you can simply call it in here. First, you have to import NumPy and pandas, and after that, you will do pd dot read underscore CSV. Already, I think you know how to import a data set CSV. Very simple. If you want many more such data sets, you can simply click on the link I have provided. I think I've not provided the notebooks, but if you just click on the link, let me just show you. All these data sets are there for you to practice. Okay. This is like a repository. You can simply download any CSV data set and you can simply start working on it. Yeah, so this is very good for practice. You can try it. Now, once you have this, then I just call the head, which is the first five observations, and they come like this. As before, we have to do some basic pre-processing on it. So we look at the column names by df.columns. We have the column names that we have. We dropped some unnecessary columns that we do not need, like the row names column, the gender column, education, age. Right. We do not need this. Why? Because they do not need factoring. They are just demographic type. What needs factoring is this A1, A2, A3, A4, A5, then C1, C2, C3, C4, C5, and so on and so forth. Why? Because we are trying to group these variables together, right? Now, again, we are assuming that we don't know anything about these variables, okay? Later on, we will find out that all the A's will be together, all the C's will be together, all the N's will be together, and so on. All right. Now, whenever there is a missing value in the row, we will drop that row, okay? So for that, we will use this command df.drop na in place equal to true, okay? And then we'll gather some information about the data frame itself, right? And look at its head. So now look at this. We only have A to O, right? That is from A1 to O5. Now we will look at some kind of adequacy test. Adequacy test means is this data fit for factor analysis? Simply. For that, the two tests that we have discussed already, the Bartlett's test and KMO test. Okay. So Bartlett's test of sphericity. For that, you need this factor analyzer, dot factor analyzer module, and from there we will import this command calculate Bartlett's sphericity, right? And from there we will get two different values, right? One is the chi-square value, second is the p-value, right? And how do we get that? This calculate Bartlett's sphericity, and within brackets you give your data frame, and it will automatically throw out two values. One is the chi-square value, and one is the p-value. And here, once you call them, you see that the chi-square value is around very high. It's 18146, and obviously a very high chi-square calculated chi-square means a very low p-value, which is close enough to zero. So, which means that the test was statistically significant, which means that the observed correlation matrix is not an identity matrix. Okay, so fine, we can do something there. Next, we have the KMO test or the Kaiser-Meyer-Olkin test. For that, again, we will use the factor analyzer dot factor analyzer module, and we will import this command calculate underscore KMO, right? And okay, so before we go that, you need to install factor analyzer package into your Python if you don't know this. So for that, I'm just writing a code here. Right, we have to write pip dot hyphen install factor underscore analyzer. Okay, so this you have to first. All right. So after this, again, when we do calculate KMO of DF, it also spits out two values. One is the KMO of all individual things, variables, and the KMO for the entire model or for the entire data set. And here we are looking at the KMO only of the individual data set, right? And we are not including all the KMO from all the other variables. So here we see it is 0.848625, right? Which is very well above 0.5 or 0.6, and it will actually factor analysis actually might be very helpful here. Okay, and it is suitable for use. Now the overall KMO is 0.84. Right, so it indicates that you can proceed with your factor analysis, and now we will have a new problem to face, which is how to choose a number of factors. Right. So one, you can use the Kaiser criterion. Second, you can use the scree plot. Most of them are based on eigenvalues. Okay. So first of all, let us check out the Kaiser criterion. So Kaiser criterion. Uh, yeah. So first, this factor analyzer command that you have. Yeah. Now that this empty factor analyzer is already there, if you want, you can also write down these n factors, 25, rotation, all these things, jibber jabber. You can write here also, doesn't matter, inside these brackets. But yeah, you can, if you want, you can try, but it's okay. It's better to do it in this way. Right. So here, what do we do? We set our parameters from here. What are our parameters? Okay. So after we have set the parameters, we fit our data into this factor analysis model, and then we obtain the coefficient scores. And based on those coefficients, now we will get what? Now we will get the eigenvalues and the eigenvectors. And as you can see, this is the eigenvectors that we have. Now, here you can see only for 6 factors, eigenvalues are greater than 1. Right? It means we need to choose only 6 factors or unobservable unobservable variables. All right. Now let us get into the scree plot. So this was the Kaiser criterion. Now that we have that, let us get into this. In here, we simply make a scree plot as we made in PCA, and look how it turned out. After almost 6 or 7, right? Yeah, what's happening? Yeah, okay. Now, as you can see, this becomes a straight line after 7, na? After 6, 7, eh, right? So if you want, you can take 7, and here, as you can see, we have prepared a data frame based on this. So here, uh, FA is a factor analyzer that we have set the parameters here. After that, here as you can see, earlier we did not have any rotation, but now we have taken the rotation to be very max, and we have taken the number of factors in factors as 6. Why? Because after 6, we are assuming that it becomes linear after this 6. So based on that, we will take 6. We can also take 7 if you want. Uh, Maybe a little more variability will be explained, but not too much. And after that, we fit the data frame to it, and then the data frame, yeah, it comes out like this. Now, from these loadings, this data frame, what did we make this data frame out of? This has been made out of factor loadings. Okay, so how do we interpret the loadings? The same way we did earlier. So as you can see, A1, where is A1 mostly headed? A1 is mostly headed towards factor 6, right? It has the highest loading in factor 6, second highest loading in factor 5.
Factor 4 is the highest loading.
Yes, hello. Uh, yes.
Yes. Factor
Yeah, yeah.
4 is.
Yes. Oh, yeah. Factor 4 is the highest. Yes, yes. Minus 0.53. So
Yes.
let us look at factor 4. Yeah. Factor 4 is high factor loadings for O1, O2, O3, O4. Okay. Let's look at O1, O2, O3, O4. Factor 4 minus 536. And here O has 0.005. Okay. They have taken inverse. They have taken inverse. Okay. So there are lower loadings. I think we have taken an inverse for that or what? 1 second. Have they taken an inverse? Maybe. 1 second. Let me just confirm. Here we have taken 6 only. Right. Hmm. I need to look at the variances. 1 second, please. If you don't click on your values. Hmm. Two, three, four, five, six, seven, five. Hmm. Okay, there are total, na? Total 1, 2, 3, 4, 5, 6. I'll put this. Total 25. We had 25 factors. 21 columns. Okay. Which one is for which one? यहाँ पे क्या हो रहा है? यहाँ पे N1, N2 आ रहा है ना? Okay, okay. So we need to change this. Okay, no problem. So this is for F1. Factor. So E highest कहाँ पे है? E is highest for factor 2. E is highest for factor 2. Okay. So let us edit this. So as we can see that factor 1 was mostly loaded, highest loading in factor 1 was by N1, N2, N3, N4 and N5. Okay. So factor 1 has high factor loadings for those. So these stand for, let's say, neuroticism according to the data set. Okay. So factor 2 has the highest loadings for, again, yeah, 7, C1, C2, C3, no, 0.0, sorry, not this one. 0.5, yeah, E1, E2, E3. 0.5968556550. So the highest loadings are for E, right? So that is extraversion. These stand for extraversion. Let's see factor 3. Factor 3 for whom is there? Highest is C. C1, C2, C3, C4, and C5. Right? So, yeah, factor 3 is okay. So, this is factor 3 stands for conscientiousness. Conscientiousness. And then for factor 4 has highest loadings in factor A, I think, in A. Is it highest? No. It is highest in A. Right. So factor 4 is for A. Factor 4 is highest for A. I think the 5 one, this will become 4, and this 4 will become 5. Let's check for factor number 5. For factor number 5, which one is highest? Yes, O is highest. 0.47, 0.49, 56. Yeah. So this is for factor 5. Yeah. Okay. And factor 6 has none of the high loadings. As we can see here in factor 6, very high loadings are not there for anyone. So maybe it has most of the uniquenesses are left here. So also factor 6 is not highly interpretable. So that means that we can also drop factor 6, right? So if we can drop factor 6, we can simply write n factors 5 and then simply from 1 to 6. Yeah. 1, 2, 3, 4, 5. Yeah. And let's see what happens. Yes. So now we have up till factor 5. Okay. Right. So this was all about factor analysis. The main thing here is the loadings plot, as you can see, and this is where all this interpretation comes from. And okay, any queries regarding factor analysis?
Is okay, sir.
Yes, yes, yes. Okay, so I'll proceed with cluster analysis now. All right. So up till now, what we have seen was that dimension reduction was being done, or grouping of variables was being done in a column wise format, right? We were reducing the number of columns. Here we will be trying to reduce the number of rows, which means that let's say you are not trying to group variables together, but you are trying to find out if you can classify a certain number of observations into different groups or different sources. Let's say, for example, like it happens in many educational institutions, in schools. There are certain schools that employ this method, that based on the marks they can in the next grade, let's say, they want to classify if they want to send a student into section A or section B or section C, right, depending on the marks they have obtained in their previous classes. So how do they do that? It means that, let's say, if there is any gradation to that, it means that students who have obtained on an average a little more marks in certain subjects, they can be told as belonging to a certain group. Or let's say a certain school wants to recommend counseling for counseling sessions. They want to recommend courses for children or courses for their students. So what they do is they monitor their academic performance throughout a series of, let's say, years, or throughout a series of sessions, and on the basis of that They want to counsel them or suggest them certain streams on whether they should pursue arts or commerce or science. So what they do is they take in their report card, uh, their marks from the previous, let's say, five, six
ঠান্ডা নেই, হাওয়া
sessions.
বইছে নাকি রে?
Yes. Hello. Yes.
Uh,
Any,
sorry, sir. Sorry for interruption.
yeah, okay, no problem. So based on that, let's say if someone wants to do that, then in that case, what do they have to do? They have to look at in the cases where the students, let's say student number one, they are seeing that that student has fared better in mathematics over other subjects. So he will be belonging to some category. Some other student, let's say he is better in, let's say, English, right? Or he is better in, let's say, biology, or he is better in, let's say, commerce. So he will be belonging to a second category. So by categorizing students on the basis of their pattern of expertise, it is easier to recommend them courses later on, right? So for these kind of problems, we generally want to cluster students into various groups. Okay. And this kind of dimensionation tool helps us, because then in that case, we do not have to look at each and every student. We just have to look at each cluster individually. Why? Because within cluster, let's say if I already do this, and if I already separate or segregate students on the basis of their their score patterns, then any group of students, 3 or 4 students within one particular group will have similar type of marks in similar subjects and will have similar interests also, right? So the variation between them will be very small as compared to, let's say, the variation between students from different clusters, right? So because of that, the intercluster variability and the intercluster distribution is often looked at as to be homogeneous across within the clusters, and it should be heterogeneous between or across clusters. So keeping that in mind, there are many ways in which this is particularly done. We'll be looking at 2 major methods. One is the hierarchical clustering method, and second we will be looking at the k-means procedure, which is a non-hierarchical method. So it is a class of techniques that are used to classify objects or cases into relatively homogeneous groups or clusters. Now, objects in each cluster, they tend to be similar to each other and dissimilar to objects in other clusters. As I said, students from a particular section will be similar to students from that section, but dissimilar to those from other sections. It is also known as classification analysis or numerical taxonomy. And there are 2 ways. Cluster analysis is more towards an unsupervised learning procedure. Why? Because there are no labeled training data on which you have to train a model. Whereas in cases like discriminant analysis, there also we are doing classification, but we already have prior knowledge or labeled data on the basis of which a model is trained. Here there is no model that is to be trained. Here we just have an organic procedure that keeps labeling on its own. Okay. So because in cluster analysis there is no a priori information, it is also known as an unsupervised classification procedure, and groups or clusters are suggested by the data itself, and it is not defined a priori. A priori means from before. Okay. So an ideal clustering situation will be like this. So let's say students having these marks are clustered in one particular place. Another students having another set of marks, they will be another cluster in another group. Now, in a practical situation, if the data is given like this, how do you plan to cluster it? That may be one thing that might require some input. So in that case, we need an agglomeration schedule which gives the information on the objects or cases being combined at each stage of the process. We need to know where the cluster centroid is, basically the mean of the cluster. because all the variables, all the other values of the variables will be centered around it. The center of the cluster, which means the initial starting points or the seeds, right? Then we have the cluster membership, which indicates the cluster to which the object or case belongs, and a dendrogram or a tree diagram, which is a graphical device for displaying the clustering results, right? Just like we see the scree plot in hierarchical clustering, we draw a dendrogram. Now, the position of the line on the scale indicates the distances at which clusters were joined, and it is generally read from left to right, right? Now, a figure is given of a dendrogram in a later slide. We'll look at that. And the distances between the cluster centers, they are how actually whether it is measured whether a particular, let's say, observation is to be allotted to a particular cluster or not, right? So we have to look at the distance between a point and other cluster centers. Then we also have an icicle diagram. Again, that will be shortly given in a slide. You can see how it looks like. At the we have a similarity or a distance coefficient matrix, right? Now, how to conduct cluster analysis? So the first thing that you need to do is to formulate the problem. Then we select a distance measure. Then we select a procedure, clustering procedure. Then we decide on number of clusters. And finally, we interpret the profile, interpret profile the clusters, and then assess the validity. So let's say we have this attitude data for clustering in this table that is given. Again, 6 different statements were given to 20 people, and based on a 7-point scale, they have answered how much they agree with that particular statement, let's say. So perhaps the most important part of formulating the clustering is problem is selecting the variables on which it is based. Now, even 1 or 2 irrelevant variable, if they are included, they might distort an otherwise useful solution. So basically here, the set of variables that have been selected, they should describe the similarity between objects, right? And the variables should be selected based on past research or theory, or basically there must be some reasoning behind it, right? Or maybe there could be a hypothesis that is being tested, and on its consideration, maybe a variable has been selected. That can also happen. In case of exploratory research, however, the researcher must exercise judgment and intuition, right? Now, the second problem, that is selecting a distance or a similarity measure. The most common used measure is Euclidean distance or the square of Euclidean distance. There are, which is very, very easy. A generalized version of Euclidean distance is the Minkowski distance. And in the Minkowski distance, there is a parameter k, which if set to 2 becomes Euclidean distance. And if it is set to 1, then it becomes Manhattan distance or city block distance. The Chebyshev distance also is a maximum absolute difference in values for any variable. Now, if the variables are measured in vastly different units, then again, as is the problem with PCA and in factor analysis, it is better to standardize the data first and then go for clustering. Otherwise, that variable which has maximum scale, that will influence the clustering more and more. So it is better to make that change before getting into clustering. Now, in these cases, before clustering respondents, we must standardize the data by rescaling each variable to have some mean. I mean, a mean of 0 and a standard deviation of 1. It is also desirable to eliminate the outliers. So again, in these cases, outliers are very common, right? And it is better to avoid. Now, to use different distance measures may lead to different clustering results. So first use all of them, but compare them first and then select one. Now, there are many clustering procedures. The most basic demarcation is hierarchical and non-hierarchical. Okay. In hierarchical clustering, there are 2 main types of clustering: agglomerative, divisible, and divisive. So what does agglomerative mean? Agglomerative means that you start with empty, no clusters, and then you make the first object that is your first cluster. The second object that you pick up, you assume that it is in your first cluster, and then you see how distant it is from your existing cluster, and then decide whether you want to make a second cluster or not. And then you take the third observation and you see which one of the two clusters it is closest to. If it is closest to the first cluster, you assign it the first cluster. Otherwise, you assign it the second cluster, and then take the fourth observation. And again, fourth observation, again, you measure which one it is closer to. If it is closer to both, if it is closer to only one of the two, then very good. But if it is farther from both, then you have to make a third cluster, right? And this is known as agglomerative. Divisive means different, back counting, which means you first assume all the data that you have belong to one single cluster, right? And then what do? You take one away from the cluster and see how distant it is from all the others, and see whether that distance from all other observations is significant enough or not. If it is significant enough, then you label it an outlier. You label it as a separate cluster or not. Okay, so that is already divisive. Then you have, among all agglomerative methods also there are so many methods, right? There are linkage methods, there are variance methods, there are centroid methods. Even among the variance methods, there is also a wards method, right? And among the linkage methods, there is either single linkage, complete linkage, or average linkage. Single linkage means, in this case, you are looking at the shortest distance between two clusters, right? In case of average linkage, you are only looking at the distance between the two centroids. And in complete linkage, you are looking at the largest distance between two clusters. Now, in hierarchical clustering, it is characterized by the development of a hierarchy or a tree-like structure, right? They can be agglomerative or divisive both. Now, agglomerative clustering, when does it start? It starts with each object in a separate cluster. The clusters are formed by grouping objects into bigger and bigger clusters, and this is continued until all subjects are members of a single cluster. So, as I said before, so it starts by assuming that everybody is a separate cluster, and then you're grouping them into bigger and bigger, bigger and bigger and bigger clusters, and this is done until all, let's say, all objects are in a separate cluster, right? Now, agglomerative research are very commonly used in marketing research. They consist of linkage methods, error sums of squares, and variance methods, right? And even centroid methods. Now, for the linkage method, again, as I said, single linkage, nearest neighbor rule, complete linkage, maximum, that is furthest neighbor approach. Average linkage is basically the different distance between centroids. Okay. So this is how it looks like. Now, the variance methods attempt to generate clusters to minimize the within cluster variance, right? So one of those methods is called the wards procedure. For each cluster, the means for all the variables are computed, and then for each object, the squared equality in distance to the cluster means is calculated, and then these distances are summed for all the objects. So at each state, two clusters with the smallest increase in the overall sum of squares within the cluster distances, they are combined. Now, in the centroid methods, these distance between two clusters and these are grouped based on those distances only. Okay, every time objects are grouped, a new centroid is computed. And of the hierarchical methods, the average linkage and wards methods have been shown to perform better than the other procedures. So again, average linkage and ward methods are what we will be doing in our Python. Okay. Now in the wards method, as we can see, you are looking at the distances of all of these from the centroid itself. And in the centroid methods, what are you doing? You are looking at the distance between two centroids. Now, the non-hierarchical clustering methods are frequently referred to as k-means clustering. Right. These methods include sequential threshold, parallel threshold, optimizer partition. So there are many ways in which non-hierarchical clustering can be done. Right. There are many new methods also that are being devised, as we say. There is this DB scan and so many other clustering ways, techniques that have come up nowadays that are all non-hierarchical clustering. And but the most famous non-hierarchical clustering method that we know is k-means clustering. So again, it is an example of a sequential threshold method, and it is basically a cluster center is selected, and all objects within that, let's say some value, some threshold value, right, some cutoff value from the center is calculated, and those that are satisfying this cutoff are grouped together. Then the new cluster center or seed is selected, and the process is now then repeated for unclustered points. Okay. Now, once this object is clustered with a seed, it is no longer considered for clustering with subsequent seeds. So this is again sequential, as I said, that once it has been clustered with a seed, it will not be considered. Why? Because it is already gone. They have passed that sequence. So now what happens if any of these let's say points come around later, then later on they might be getting another chance. Let's say after being clustered with the seed, right? But not in that particular instance. There is another method called the parallel threshold method. It operates similarly, except that several cluster centers are selected simultaneously. Right, and objects within this threshold level are grouped to the nearest center. And then there is the optimizing partitioning method, basically, which means you are partitioning them and you are trying to find out which is the best kind of partition, so that overall, criterion is optimized. Hello, am I audible?
Yes, sir. Yes, sir.
Yes.
Yes, I'm actually sorry. There's a power cut here, so but don't worry, I'm on the data. Yeah. Okay. So now the choice of clustering method and choice of distance measure are interrelated. So you can use any combination you like, right? And based on that, we can then use whichever combination of techniques is giving maximum profit. Now, this is the agglomeration schedule that is used by Ward's procedure, right? So in stage one, let's say the first cluster 1, 14 and 16, they are getting combined, and this is suppose their coefficient, and next then we move on to stage 2. Again, observation number 6, observation number 7, their coefficient is given 2, right? And then on the next stage, let's say in stage 6, you have 10 and 14, right? So here 6, 7, 1 second. Number 1, 14, number 2, 16, and then you have a coefficient of 1. After that, the next stage is 6, Then you have 7, you have a coefficient of 2, and in the next stage you have 7. Okay, so this is just the scheduling part, no? Okay, okay. This is just the scheduling. Okay, okay. This is the stage cluster first appears. Okay, so this cluster then first appears, this 14, 16 first appears in the sixth stage. So this 10, 14, this is also coming on to the first cluster. Okay. And then clusters combined in the stage 2, 6 and 7 are combined, cluster 6 and cluster 7, with a coefficient of 2. And on the next stage, again, it is 0, 0. So which means the next stage it is at number 7, which is 6 and 12. So 6 and 12 and 6 and 7. The 6, 7, and 12 are in the same cluster. And they have been clustered around in 10.1667. Here, the first cluster already has two new, let's say, things, two new observations. And in the next stage, which is at the 10th stage, you have 1 and 6 again, right? So when you have 1 and 6 again you have cluster 1. Initially, you had what, 3, right? And now you have a total of 6. So based on this, again, sequentially only Watt's procedure will go forward. Now, these are the membership of cases using the Watt's procedure. So if you are looking at the label case, so if you are looking at, let's say we have 4 clusters, then 1, 2, 3, 1, 3, 2, 1, 1, 1, 2, 3, 2, like this it will go on. If you have 3 cases, so you have 1, 2, 3, 1, 2, 3, 1, 2, 3, and so on. There is only 1, 4 here. And if you have 2 cases, 2 number of clusters, then 1, 2, 1, 2, 2, 1, 2, 2, 2, so something like that. Okay. Now this is the vertical icicle plot, right? Which means that if this is the number of clusters and this is the observation type, then in which cluster, up to which cluster number does this particular observation wait for until getting into until getting selected. And this is known as what we call a dendrogram. Okay, this is a rescaled distance cluster combination. And in this case, as you can see, if we make a cutoff at, let's say, 15, or a little later at 16 or 17, we will be getting that basically there are only 2 clusters that can be formed. Whereas if you keep the rescaled distance above 10 or below 10, in this case, then you will look at three different uh, three different clusters. One is this cluster, one is this cluster, and one is this cluster. Right. So obviously, if the distance clusters combined distance cluster is high enough, which means above 15 to 20, uh, we then it might be okay. I mean, because then you have only 20, only two clusters, two classes, right? 0 or 1. So that's easier to handle and easier to interpret in some way. Now, how to decide on the number of clusters? There are many criteria, right? But there are certain practical considerations that you might need to grasp. Now, in hierarchical clustering, the distances at which these clusters are combined, they can be used as criteria. Now, this information can also be obtained from agglomeration schedule or from the histogram itself, right? But the ratio of total within group variance to between group variance can be plotted against the number of clusters. The point at which an elbow or a sharp bend occurs, this indicates the appropriate number of clusters. So as we said, we look at something like a scree plot. So we'll also make something similar to a scree plot here. It's not exactly a scree plot, but something similar. And the relative sizes of the cluster should be meaningful. So that, again, as I said, standardization is necessary. If you don't do, better keep in shape. Now, By keep in shape, I mean keep the data set in shape. Yeah. So it means that basically do not allow one variable to have very high variance and the others to have low variance. So that's it. Now, for interpreting and profiling the clusters, we need to examine the cluster centroids, how far away they are from each other, and then we assign it a particular name or a label, and then we discuss. It is often helpful to provide these clusters in terms of variables that were not used for clustering. Now, this might include, let's say, demographic, psychographic, product usage, media usage, other variables, and look at the means of the variables that we have. In cluster number one, mean is 5.75, cluster two 1.67, cluster three 3.5, and in the sixth one, cluster one 3.85, cluster two 3.33, and cluster three 6. Right. So what was it? Because of this, as you can see, cluster number three has higher values in these V4, V5, V6. Right. And it also has higher values in V2, but yeah, V2, V4, and V6. V2, V4, and V6, anybody has? I think so. That is. And then V1, V1 and V3. Yeah, I think V1 and V3 belong to cluster number one. V2, 4, 5 is him. That's V2, V4, and V6. Yeah, 5.83, 6, and 6. These are for cluster number 3. V1 and V3 for cluster number 1. And that leaves us with V5. Right? Again, 5.5. And here we expect cluster number 2 to come in. Okay. Now, how to assess the reliability? So you can perform this same analysis on different distance measures and then compare. That is number one. Number two, after clustering is done, based on the clustering, you can make let's say various things. For example, uh, in this case, let's say you are performing cluster analysis on the same data using different distance measures. Let's say you are changing the value of k, and then you are simply seeing that for which value of k or in Minkowski distance it is giving the best classification, right? Or let's say some performance metric of some classification algorithm. So in that case also you can look at it through that way. Every time you perform that analysis using different value of k, what performance metric comes up, and or then optimize it simply. That can be done. Then yeah, the fourth point under this, how to do it, is to delete variables randomly. Performing clustering based on the reduced set of variables. Right. You have to compare the results with those that have been obtained by clustering based on the entire set of variables. And in non-hierarchical clustering, the solution, it might even depend on other cases of the data set. Right? So it is better to make multiple runs or use different order of cases until the solution stabilizes by itself. Now here are some of the results. As you can see in V1, we have in cluster 1 we have 463,727. Right? In cluster 2 it has 232,472, and in cluster 3 it has 726,413. So as you can see in cluster 1, 7 and 7 and 6. So V2, V4 and V6. Right? V2, V4 and V6. That is it. And then you have in cluster 2, you have V5, which is pretty high. And in cluster 3, you can see so variable 1 for number number 3, V2. V2 is I think for the first cluster, but I already at 4. Right. So in that case, uh, you see this V3, this can be thrown off. Yeah, so this highest is 6 here. Okay, so this also goes to cluster number 3. For variable 2, we are adding it to, let's say, cluster 1 because it has 6 value. It has 6 centers, right? In V3, there are 6 centers in Surat, and 4 V4 is Rawaji. Right. This yeah. और जाहिर है. Yes, ये. Okay, so as I said, V2, V4, and V6 are for 1. So this is V2, no problem. V5 contains V2, only second cluster. तो यहाँ पे सिर्फ 2 और V6 में भी हमने देखा कि इस तरीके से right. So we have 7 here, 2 here, and yeah. Now, has there been any change in the clusters in the iterations? So in this way, we can actually make changes also. So the first stressness change was like this. Now, after the second iteration, the cluster changes, the cluster chambers have become 0, 0.0, 0, 0.0, and 0, 0.0. Right. All right, let's move on. And as you can see, they are measuring the distance between each cluster, between each case and the cluster, and based on that distance, they are finally allotting values to each cluster they might go back to. Hmm. So now let us get into some of the coding part. Right. So for cluster analysis, we are using the same breast cancer dataset because we don't have much time. And we quickly import NumPy, Pandas, Matplotlib for the plotting part and sklearn.datasets. And from there, we'll import the load breast cancer, same as before, and the same. Now, just before we get into the clustering portion, right, what we do is simply for making this dendrogram for hierarchical data, for hierarchical clustering, scipy.cluster.hierarchy. From this module, we have to import two things. First is the dendrogram, and second is the linkage. Right. Once you do this, then you need to write for sklearn.cluster module. Right. We have to import agglomerative clustering. And after this, after you have combined this, then already linkage command you have called. So now it will generate the linkages of the data that we have. I have named it df. Method we are using is wards method. So write down method equal to ward, and the distance we are using is Euclidean distance. So simply write down metric is equal to Euclidean, and then write down dendrogram of the linkage data. And once you have that, Look at it, right? Now, if you want, you can add some points here that if we are looking at a cutoff here, then in that case, 2 is sufficient. But if we are looking at a cutoff here somewhere, then I think further scrutiny needs to take place based on where the cutoff needs to be on the tree. Now we will simply generate the bivariate labels. As we have seen here, the cutoff needs to lie here. So let's say the number of clusters that we have decided is 2, because as you can see, these two groups, the red and the green groups, are far separated from each other. So that is why it is better sometimes to have these 2 clusters only, right? Because within cluster also they need to get assimilated. So between clusters uh, might be a problem. So based on that, here we are simply taking the predicted value of the fit, which means for every row in DF should be assigned what cluster, right? And the labels we are saving here under labels, and then I'm printing them here, right? So what does this mean? This one means the first observation should go to cluster 1, second observation cluster 1, third observation cluster 1, fourth observation cluster 0, fifth observation cluster 1, sixth observation cluster 0. So by this way, whichever is 1, with that number observation will go to 1, and the other observation will go to 0, and so on and so forth. Okay. Now this is for this was for hierarchical clustering. Now we will look at k-means clustering. For k-means clustering, you need to download the this sklearn.cluster thing, this module, and from this module, you need to import the k-means command. First, what you need to do is to introduce, or to first simply write down a blank list or a blank array or a blank collection like inertias, and then append the value of these inertias with a looping factor. So after I define this empty vector or an empty list, I simply get into a loop, a for loop, right? That is from 1 to 11. It will run from 1 to 10 actually, and from 1 to 10 it will take values from k-means, and this n cluster means number of clusters. So every time a loop runs, it means that I will increase the number of the cluster and then do k-means and see what the fit is. Okay, and then append it this inertia. All right. Now, after I have done this, what I have done is, for each of these cases, these inertias, I have plotted them. In our x-axis, I have taken 1, 2, 3, 4 up to 10. And in our y-axis, I have taken all these inertias that have been collected over here through this loop. And then I have written the title of the plot as elbow method. The label x is the number of clusters, and the y label is that of inertia. And this will give us something like a scree plot only. So as you can see, as you go down, or as you go to number of clusters, the inertia is also decreasing. And as you can see, after 4, it becomes more of a linear thing. So I would recommend maximum number of clusters you should keep is 4, right? But in this case, even if you keep 2, so in this case, k means we are taking 2 clusters. Obviously, lower the number of clusters, lower the grouping, and more you can interpret, right? A more clearer will be the demarcation. So I'll simply write down k means as it is, Why? Because I've already imported it in the previous this one, right? And after that, I will include that number of clusters is 2. Okay. Once I include that, it means now I can feed the data into it. I'll feed the data into it. And then what do? I plot the scatter plot. But here I could have done it for all particular columns. But here I'm not doing it for all columns because there are 30 odd columns here. So what I'm doing is, because it is a 2D figure, I am picking out two columns. One is mean concavity, and one is mean symmetry. If you can see earlier from the earlier slide, I have taken this mean concavity and mean symmetry, I think. Mean symmetry. Right. These two variables only I have taken. I have not taken the other variables just because I just wanted to show you how it is done. Okay. So once that is done, here color will be based on the k-means labels. Right. So if the k-means labels is 0 and 1, so the color will be based on those labels. And then we will just show. So here you have this. So as you can see, because we only have two variables, right, there is a sincere overlap. But you can see that as you go towards the higher x variable, there are a lot many more yellow ones than here, right? Same goes for hierarchical clustering. What we do here, we will take the labels, but the labels that were made on the basis of hierarchical clustering we have taken only, not that of k-means. Okay, this one was done by k-means labels. My one was done by the label that we had procured from hierarchical clustering before. I'll show you this one, right? And based on that, as you can see, there is this overlap here again, almost similar as this one. So again, there are many other ways, many other things you can try. Instead of Euclidean, you can try out the Chebyshev distance. You can try out Manhattan distance. Instead of word, you can use linkage and all these things. I have tried to keep it as simple as possible here so that there is lesser scope for confusion. But again, as I said, it is more about practice than anything else. If you keep practicing on different data sets and keep honing your programming skills, then that day will not be far when you'll be a better researcher day by day. Now, up till this, I think is enough for you to know about cluster analysis, because we have already decided on the number of clusters, and we have seen how the clustering will label each observation in the data set, right? And with this, I think we have covered the very basics of the three topics that we had started out with. I hope I have been able to at least try to alleviate the fear of multivariate analysis, if not
Yes, sir.
anything
Yes,
else.
sir. Today, very nice session. Thank you very
Uh,
much, sir.
yes,
Very
if
nice.
there are any doubts, my